So today we're talking about growth and decay. This occurs in nature naturally. You guys probably know that bacteria is like in most cases, a single cell organism. So if you have 100 bacteria, that means you have 100 single cell organisms. Well, the way that they reproduce is that the cell just grows bigger and bigger and bigger, and then it splits in two, right? And so the bacteria has kind of like a doubling growth or whatever. So that would be growth. And then decay is something like radioactive material, half-life. So the half-life of some sort of radioactive material means that after a certain amount of time, the material is 1/2 of what it was. So that's an interesting dynamic. And these things occur in nature, so we need a mathematical model that kind of represents that so we can make predictions about things. So to complete this table, there's a couple ways you could do it. You could do these by hand. I don't know if we do enough of this, but when I go to evaluate -1, what I'm going to say is y equals 2 raised to the -1. Well, we know that's 1 over positive 2 to the 1. So in other words, when x equals -1 for this function, my y value equals a positive 1/2. How many of you guys got that? Okay, good. So then for the next one, if I say y equals 2 to the 0, anything raised to the 0 power is just 1, so we'll put a 1 here. Then the next one, and so what I'm doing is I'm just plugging in these values for x, right? These are the input values. Maybe we should write that down. That's the input values, and this is the output value. This is the domain. Oh, man. And this is the range. The x's are the domain. So the next one is 2 to the 1, which is just 2. Okay. And then the next one is 2 to the 2, which is 2 squared, which is just 4. Okay. How many of you guys got those? All right. Now you could plug them in the fancy calculator if you wanted to double check your work. So let me just show you how to do that real quick. We'll make it big so you guys can see it. Well, maybe. All right. So if I go into y equals and I say 2 to the x, and then I can go to second table, notice that when x equals -1, I get 1/2 or 0.5. When x equals 0, y equals 1. When x equals 1, y equals 2, and so on and so forth. So that's how I double check those. Let me take a screenshot of that so you guys can see what we're doing here. Actually, let me do this. Let me include the x and y in there. So this example is going to be a little long because I got to talk about growth and decay, and I'm going to do it all in one cohesive kind of thing. So this is, kind of what we're talking about, right? The calculator verifies what we did by hand. So now let's do the other one. So I'm going to say y is equal to 2 times 3 raised to the -1. Well, that's 2 times 1 over 3, or just 2/3. So we'll say 2 over 3. The next one is y is equal to 2 times 3 raised to the 0, which is just 2 times anything raised to the 0 power is 1. So that's just 2. Next we have y is equal to 2 times 3 raised to the 1, which is just 2 times 3, which is just 6. And then lastly, we're going to say 2 times 3 squared, which is 2 times 9. Remember, we got to follow order of operations. You're going to do the exponents first. So we get 18. Okay. And so if I come in here and change, or I'll do the second one. Well, no, let me just change it in here. Times 3 raised to the x. Now when I look at my table, yeah, I know that. I was going to do it that way, and I was like, I don't want to. I wanted to keep them separate. So, I don't know where we'll make that fit. We'll just put that here. Okay. One thing I'd really like to point out, though. Notice, what do I do to get from 1 to 2, or from this term to this one? I'm multiplying by 2, right? What's 1/2 times 2? 1. What's 1 times 2? 2, right? Kind of lost my things here. Okay. So, to get from here to here, I'm multiplying by 2. To get from here to here, I'm multiplying by 2. What's 2 times 2? 4. So I'm multiplying by 2. By the way, that's my base. Now if we come over here, what's 2/3? How do I get 2/3 equal 2? Well, I multiply by 3. Over here, 2 times 3 is 6, so I multiply by 3 again. Over here, 6 times 3 equals 18. That's the base. So in this particular one, the base is equal to 3. Okay, so those are little tricks that you could do. These are all connected. So then what does this mean? Well, it says that an exponential function has the form y equals a times b raised to the x, where a cannot equal 0, otherwise it's just 0, and b is a positive real number other than 1. If a is greater than 0 and b is greater than 1, then it's exponential growth. B is called the growth factor. So this would be the growth factor of 3. You would say growth factor of 3. And then over here, we would say that this is a growth factor of 2. Okay, so I'll leave that up there for a second and let you guys write that down. Then we got to go to the next slide. But in order for there to be growth, if there's a doubling effect, right, that would have a growth factor of 2. If there's a tripling effect, that would have a growth factor of 3. And we call it growth because you're multiplying by a number that makes the next number bigger. In other words, it increases. 1/2 to 1 is an increase. 1 to 2 is an increase. 2 to 4 is an increase. Well, how much of an increase? By a growth factor of 2. Over here, 2/3 to 2 is an increase. 2 to 6 is an increase. 6 to 18 is an increase. So we call it a growth factor because we use this for modeling, right? So human beings make other human beings, so there's a growth factor. I think in the US it's like 2.1 or something like that. It may have changed, but in other words, that for every family, mom and dad might make 2, 3, 4 kids, and it averages out to be 2.1 or 2.2 or something like that. Bacteria is generally a doubling effect or more and stuff like that. We have exponential growth in a lot of things in nature, so this is how we actually make the predictions. This is how we know how much stuff we need. Okay, so can I move on to the next slide? Okay. All right, so then what about, what does that mean? Well, let's look at it, okay? And so I want you to sketch this out real quick. Now, you don't have to write it verbatim, but the parent function, and we've talked about parent functions a lot, is the simplest, most basic version of the function, right? Just the base function, right? In this particular case, it's just b raised to the x, where b is called the base, okay? So that's our base. That's and by the way, the base is the actual growth factor, okay? But the growth factor, it's called the growth factor if b is greater than 1 growth, because the next number will be bigger if I multiply it by something greater than 1. You could be 1.1, but that next number will be slightly bigger. It could be 10. It just depends on what's going on. And so let's talk about what the graph of a growth function looks like. On the parent function, our x-axis is the asymptote. An asymptote is a line that approaches more and more closely. So what they're saying is this blue line is never going to cross 0, but it'll approach it. Remember, this little arrow means approach, or approaches. So what they're saying is that as x approaches negative infinity, in other words, if I go this way, that little blue line, if I follow this curve this way, and I go on forever, my y value will be close to 0, but it never crosses 0. It approaches 0. But then, as x approaches positive infinity, in other words, as I go to the left, f of x, and remember we said the f of x is really like y, right? Grows. And it'll grow towards positive infinity. So over here, whenever we say x approaches negative infinity, that means we're going to go to the right. So there's two things we got to keep track of. The infinity, 0, positive infinity, negative infinity. When x approaches negative infinity, that means you're going to the left. When x approaches positive infinity, that means I'm sorry, I said that backwards. Why did I write them down backwards? I know why, because I'm looking out. I wrote them down backwards because I was thinking backwards. This is going to the right, sorry. And this is going to the left. All right, so the domain f of x is all real numbers. In other words, there's no domain restriction. Remember, there are only 2 domain restrictions in Algebra 2. You can't have 0 in the denominator, and you can't take an even root of a negative number. Everything else is all real numbers unless defined by special parameters. Okay? All right, cool. So then, does everybody have this written down? So the next thing is to think about what happens. Can I move on to the next slide? Or maybe, yeah. Is that a yes or no? I can wait. So the y value, which is really f of x, I got to quit writing stuff down. That's the problem. remember that the y value is really f of x. So put that in there somewhere. It grows over time. All right, I'm going to move on to the next slide now. Can I? Is everybody still writing it down? I can wait. All right, so then what happens when b is a fraction? So remember, a has to be greater than 0. If a is negative, remember when a is negative, it flips it, right? It's just going to flip it like this. That's what a does when a is negative. But if b is a fraction, and I should probably say positive fraction, then it's called decay. Well, what does that mean? Well, let's look at one. So the parent function for this occurs when b is some sort of fraction. So remember, when we say as x approaches negative infinity, that means we're going to the left. Well, now, if I look at this and I go to the left, it's going to grow. But we don't read a graph from right to left. We always read it from left to right. So as we go to the right, now it approaches infinity. And think about that. Whatever this number is, it's gonna, when I multiply it by a fraction, it's going to be a smaller number. And when I multiply that number, we're talking about the y values, or f of x. When I have a growth factor and I multiply this y value by a fraction, it's going to be smaller and smaller and smaller and smaller. But it'll never equal 0 because a is greater than 0. Well, in this case, a is equal to 1, right? Well, what about the domain? Well, in this case, the domain is all real numbers again. And the range is y is greater than 0 again. Okay. So the shape of the graph is different. So this can represent a lot of things. The most common one is radioactive decay. So isotopes are not stable, so they give off particles. Over time, those particles, it gives off a little bit more, a little bit more, a little bit more, and that's where a concept like half-life comes from. The half-life is how long it takes for the material to be exactly 1/2 of what it was. So when we talk about carbon-14 dating, that's how they date really old stuff. In the environment, the sun does some things, and it makes carbon, which is usually 12, makes it a carbon-14, but carbon feels best when it's at 12. So there's some extra stuff that's done to carbon. And we have carbon-14 and carbon-12 in the environment. But an organic, well, or inorganic, but any material that has carbon in it will have a combination of carbon-12 and carbon-14. The more carbon-14 we have, the younger it is, right? The less carbon-14 you have, the older it is. And the half-life on carbon-14 is 5,700 years. So if I have 1 gram of carbon-14 and I just let it set on that table for 5,700 years, after that time, I'll have a 1/2 gram. Because the particles, those little extra particles would just kind of leave because they don't belong there, and it's just something that happens in nature. Okay. Now we can model that growth by a decay function. Depreciation of a car, right? The value of a car goes down over time. So think of anything over time. Can you guys think of an example that the value goes down over time? A car is a great example, right? A car is a great example. So we could model that decay over time. And radioactive decay works the best. Okay? All right. So what I'd really like to do, well, not here. Do you guys have this written down? Yeah? Okay. Let's go here. Well, let's see what those look like with real numbers and stuff. Okay? Well, we already know it says tell whether the function represents exponential growth or decay. So the way that we do that is if b is greater than 1, it's growth. Now, if b is between 0 and 1, that means that it is a positive fraction. That's a horrible letter. All right, positive fraction. Well, then that is decay. And remember, when I say b, we're talking about a, b, x, where b is the base, the thing raised to the x power. So here, b is equal to 2. Well, that means that b is greater than 1 because 2 is greater than 1. So this is growth. Now, I already know that if I were to graph this, and I'm going to help you guys a little bit with graphing. So let's graph this in a second. Well, let's graph it now because we know the values, right? So when it comes to the graphs, on our test, when you guys graph stuff, you're not as precise as I would like you to be. Because the precision matters, right? So this is my x-axis, this is my y-axis, and remember y really means f of x, because these are functions, right? And so we know based on our table of values that we did on the previous when x equals -1, y was equal to 1/2. When x equals 1, or 0, y equals 1. When x equals 1, and from this point you just double it, right? So 1 times 2 is 2, and then when x is 2, 2 times 2 is 4. When x is 3, 4 times 2 is 8. Okay? So I'm just going to graph those points. I'm going to go -1, 1/2, right? Because this is -1, and this is +1, and this is 2, and this is 3, and this is 4, 5. Whoops. Wrote 5 twice, or 4 twice. And this is 6, and this is 7, and this is 8. And maybe I'll plot these points in a different color. So that's -1, 1/2, 0, 1. Then over here, this is 1, 2, 3. So then when x equals 1, y equals 2. So that actually goes right about there. Then when x equals 2, y equals 4. So that goes right there. And then when x equals 3, y equals 8. So I'm going to go over 3, up 8. And I know that it approaches That's how your graph should look on the test. And then you should label these. This is 3, 8. This point right here is 2, 4. This point right here is 1, 2. This point right here is 0, 1. And then this point right here is negative 1, 1/2. Okay? Now, on the other side of this, we're going to do the next one, which is, let me change the color. B is equal to 1/2. Well, 1/2 is between 0 and 1. So this is a decay. So we already know how this is going to graph. So let's label this real quick. Well, let me do my table of values. X and Y. So when I plug in negative 1, remember that's going to be 1/2 raised to the negative 1, which gets flipped. That's just going to be 2. And I'm going to put in some different numbers. Actually, let's do negative 1, 2 down here. So when I do negative 3, that's going to be like 1/2 raised to the negative 3, which is going to be flipped, right? That's going to be 2 raised to the positive 3, which would be 8. When I get negative 2, that would be 1/2 to the negative 2, which is just 2 to the positive 2. So that would be 4. When I plug in 0, that's just going to be 1/2. And so what I'm doing to get from here to here, notice that I'm just multiplying by 1/2. So I could do this without doing the math. What's 1/2 of 1/2? 1/4. Okay. So now to graph this, I'm just going to come in. Basically the same thing. I'm going to make my y-axis. Then I'm going to make my x-axis. This is y, but remember, y is really the same as f of x. So I'm going to plot the first point. The first point is going to be negative 3. So I'm going to go over 1, 2, 3, and then I'm going to go, let me label this real quick. This would be 1, this would be 2, this would be 3, this would be 4, 5, 6, 7, 8. And then this is negative 1, this is negative 2, this is negative 3. So I'm going to come in here and I'm going to go up to the left 3 and up 8. So that's the point negative 3, 8. Then the next one is going to be negative 2, 4. So I go over negative 2, up 4. So that's negative 2, 4. Next one's negative 1, 2. Negative 1, 2. Then 0 is at 1/2, so that's right here somewhere. And then 1 is at 1/4, which is like right here. So we have 2 that you can't really see, but this is 0, 1/2. And then way down here we've got 1, 1/4. And so when I draw my curve to fit those, and we know that it will never ever cross 0. And so I've got this here, Okay? And I think that's all we're going to do for today, because we're out of time anyways. So I'll leave that up there for you guys to finish writing that down.